Hello, I'm Yulia Svetashova. I'm a PhD candidate at Robert Bosch Corporate Research. I'm presenting the joint work of Baifan Zhou, Tim Pushinsky, Stefan Schmidt, Evgeny Harlamov, and mine. I will show you our tool called SemML and our approach to reusable machine learning models for manufacturing. SemML enhances traditional machine learning workflow with semantic components that help us understand and describe manufacturing processes, integrate the data, and automate machine learning modeling. Its starting point is the core ontology for manufacturing. Core ontology is linked to the machine learning ontology, and for each data type property in the core, we defined its corresponding type in machine learning. For example, sensor measurements collected during the process will be treated as time series features in machine learning. Equipment wearing statuses will be count features. For each feature type, we have defined different pre-processing and feature engineering strategies, and we can describe concrete machine learning pipeline configurations and store them in a catalog. The machine learning backend can execute these pipelines automatically, taking as input annotated datasets. Thus, the integration of each new dataset is reduced to its annotation. The integration of a new manufacturing process is a description of this process in terms of the core ontology for manufacturing. In this demo, I will highlight the functionality of the tool that enables the reuse of the developed models for new datasets, new monitoring tasks, and new processes. I will show two of its components, Ontology Extender and Domain Knowledge Annotator. Let me first walk you through the example machine learning pipeline we'll be reusing today. In this pipeline, we have our input features, data from a production line, single features, and time series. We will predict some quality indicator. In pre-processing, we perform simple feature engineering operation on the time series. For each sensor measurement curve, we extract 8 statistical features, minimum, maximum, mean, median value, and so on. The extracted statistics will be concatenated with single features. Then we split the data into the training and test data. Then we normalize the data and perform feature selection. The selected features will become an input to the machine learning modeling. The quality indicator will be its output. Finally, we will train the model with a simple linear regression algorithm and test it. This is the visualization of our example pipeline. Let me show the stored configuration for it. The pipeline is loaded into our workflow configuration tool. You see our features, then the processing strategies. Time series statistics will be concatenated with single features. Concatenated features are split into training and test data. Then normalization step follows, and finally feature selection. So these selected features will become the input to the linear regression algorithm in the modeling stage. We will use the model with our first dataset to predict the quality of an operation in resistant spot welding. Now I'm using Ontology Extender to create the description of the process. This manufacturing process consists of consecutive operations. The resistant spot welding operation is performed by a welding machine. It connects several metal sheets in a raw product. And a raw product can be a car chassis part, for example. The chassis is an assembly and has two components, top metal sheet and bottom metal sheet. They are uniformly described as physical entities with their geometry and material properties. The product of this operation is a welding nugget. Its diameter is an important quality indicator. Ontology Extender has templates to create ontology terms for machine characteristics, software programs, sensor measurements, and quality indicators. When we are finished with the description, we can switch to the domain knowledge annotator. Here we simply map the raw variable names to the terms in the domain ontology we have just created. We select a template group and a class from the drop-down list, and all the data type properties where the class is a domain become available for annotation. Now the input to the machine learning pipeline is ready. We go back to our workflow configuration tool and load the data. It comes in multiple files. Then we load the mappings we created in the domain knowledge annotator. and infer their feature groups for all variables. The pipeline is pre-configured and we can go directly to the modeling step. We train and test the model. It's finished and we can plot the estimated diameter values against the actual ones. The model fits well and we continue with a new dataset. The new resistance spot welding dataset comes from a slightly different production line. The quality monitoring task remains the same, but the car chassis contains a 3-component assembly. In the ontology, we have 2 sheets, top and bottom. We will add the middle sheet. Analogous to that, we can reuse the machine learning pipeline developed for the robust control system to the adaptive control system, and also describe new sources, simulation and laboratory data. After extending the ontology and annotating the data, we'll have a different set of input features, but the machine learning model configuration will just work with this input. In the Ontology Extender, we add a middle sheet and link it to the car chassis. Now this assembly has 3 components: top, bottom, and middle sheets. We can go to the domain knowledge annotator, and all the classes and properties we have created are in the drop-down lists. The user can actually start with the mapping of data and switch to Ontology Extender every time when a term is missing. The navigation browser here has identical groupings as the templates panel in the Extender. When the mapping is finished, we load the data to our workflow configuration tool. We load single features and time series. We load the mappings and infer feature groups. We then run the pipeline with all the feature processing and feature engineering stages, train and test the model, plot the estimated diameter values against the actual ones. Finally, we store the visualization and continue with our last scenario. Potentially, many observed parameters of the operation and wearing characteristics of the equipment can serve as quality indicators. For example, the spatter during the operation can signify poor quality. And of course, various methods based on sensor fusion are constantly developed. Bosch has a special Q-value that relies on statistic features from sensor data. It's a calculated parameter, often present in the datasets. In our scenario, we'll observe how we can change the quality monitoring task and make our pre-configured pipeline work for predicting Q-value instead of nugget diameter. As the input to our machine learning pipeline, we will use the dataset from the previous scenario and change the target variable. The template for quality indicators allows to add the quality-related properties to already existing status parameters. It is a natural task for a data scientist to test what can be a reliable quality indicator in a dataset. For the column in the data that is annotated with these properties, the system will infer the feature group quality indicator and make it a target variable. Thus, we can reuse predefined configurations and test what works best. We load the data into the machine learning environment. In this iteration, the Q value will be the quality indicator to predict. We infer feature groups, trigger feature processing and feature engineering, train and test the linear regression model. We can plot the estimated Q values against the actual ones, and we're done. The cycle of data preparation for a new manufacturing process will have the same 3 stages: ontology construction, data annotation, and model reuse. Data scientists use annotated data as the input to the pre-configured machine learning pipelines, select those with a good fit, and explore various quality indicators. The workflow of pipeline reuse we showed in our scenarios is based on the formalized domain knowledge and domain-specific feature engineering. It largely speeds up the development of the machine learning models for condition and quality monitoring. Thank you.